this lecture, we'll be discussing regression models. A quick recap. Last time we talked about two main categories of predictive modeling techniques, including supervised learning and unsupervised learning algorithms. For supervised learning algorithms, we work with data sets which have target value or labels. But for unsupervised learning algorithms, the data set do not have any target value, and instead we want to find the hidden structure in the data set. We also discuss four main steps for predictive modeling, including data pre-processing, learning algorithms, evaluation, and prediction. We mainly focused on pre-processing techniques for both univariate analysis and bivariate analysis. For univariate analysis, we can look at box plots, we can look at descriptive statistics, and also handle missing values for each variable. For bivariate analysis, we looked into pairwise correlation to identify highly correlated variables and also some visuals like heat map and a cluster map. In this lecture, we focus on multiple linear regression, lasso regression and ridge regression models, elastic net, which is a combination of lasso and ridge regression models, and finally, logistic regression. There are two main libraries in Python that can be used for predictive modeling. The first one is scikit-learn library, which provides a range of supervised and unsupervised learning algorithms. Majority of machine learning algorithms are defined under this library. There is another library named statsmodel, which contains more classical frequentist statistical models. Now I start off with regression models first and go over a couple of examples. For the first one, I use a statsmodel as a library, and for the second example, I'll be using a scikit-learn library. So a quick review on regression analysis. Regression analysis is a statistical methodology that utilizes the relation between two or more quantitative variables so that one or several variables can be predicted from the others. So there are two types of relationship, functional relationship and a statistical relationship. When we are dealing with functional relationship, for each x value, there is one and only one y value, and that's the definition of a function. But when we are dealing with a statistical relationship, as you can see in this figure, for each level of x, there can be multiple y values. And instead, we can collect different data points at each value of x and look at the distribution. And if we find the mean value at each level of x and connect them, then that becomes the regression model. If it is a curve, then we have a regression curve. If it is linear, then we are dealing with linear regression models. Overall, there are two types of regression models, multiple regression and multivariate regression. In this course, we focus on multiple regression, means that we have several independent variables and we want to predict one response variable. But for multivariate regression models, we can have more than one response variables. And here you can see the equation for multiple regression. Beta 0, the intercept, plus beta 1 x sub 1 through beta k x sub k. So it means that we can have k independent variables and we can use that to predict the value of response in here y. I would like to go over the assumptions of multiple linear regression. It's important to understand the assumptions, and we need to check this assumption when we fit regression models to make sure that regression model is the right statistical tool for your data set. The very first assumption is that there must be a linear relationship between independent variables and response variable. And to check that, you can look at the scatter plot. If it's not linear, then linear regression models are not suitable. The second assumption is that independent variables shouldn't be highly correlated with each other. And that's why we look at the pairwise correlation for pre-processing phase. One critical assumption is that independent variables are independent and are not highly correlated. The third assumption is that the variance of error terms are similar across the values of independent variables. To check that, we can look at the plot of standardized residuals versus predicted values, and we can see if the points are equally distributed. The last assumption is that multiple regression assume that residuals are normally distributed. Now, to estimate the coefficient of linear regression models like beta values and the equation that we just saw, we can use ordinary least square methods. It means that we can define a function which measures the error, for example, sum of a squared error, and based on that, we can estimate the coefficients. For linear regression models, inputs can be numerical or categorical data, but outputs are numerical. Now, let's look at the first example, and we want to use the stats model API to solve this problem or fit the regression model. Stat models is a Python library that provides functions for the estimation of many different statistical models, as well as for conducting a statistical test and a statistical data exploration, for example, analysis of variance and various statistical techniques we learned before. In this example, first we import the libraries that we are going to work with, including numerical Python, matplot library for visualization purposes, pandas for data frames, and statsmodel.api. Then we generate x and y. Here, x to generate data points for our independent variable, we are using lean space method, which generates evenly spaced observations between for an interval. So 50 data points which are evenly spaced between 1 and 7 in this example. Then y is a function of x. And here, let's say it's 3 plus 2 times x plus 1.5 times a randomly generated number from a standard normal distribution. Then we create a data frame which has 2 columns, 1 column x data and 1 column y data. And then we want to call the stats model, use the ordinary least square technique or OLS, and then we pass y and x as input to that method and feed the regression model. And after we create the model, then we can apply predict method to make the predictions by the model, and we can print model summary, because in a statistical analysis we want to look at the significance of each coefficient. We want to look at the R-square values and p-values. Now let's implement this in a notebook and you can see what the result look like. So we import libraries. We import matplot library as PLT. We import pandas as PD. We also import the stats model API as SM. Then we generate x and y data points. We use line space, 50 observations between 1 and 7, and they are evenly spaced. And y value is just a function of x. 3 plus 2 times x plus 1.5 times a random number np random dot rand n, which generates random numbers from a standard normal distribution, and we pass length of x. So if we print x, you can see it's an array between 1 and 7. Y is also an array to the function of x. Then we can create a data frame to combine x and y in a table. we use dictionary. The first column is X data. The values are equal to X, and the second column, let's say Y data, equal to Y variable. Now we have a table with 2 columns, and then we can create a model object we call the stats model. Then we apply the OLS technique, ordinary least square technique, to estimate coefficients for our regression model. We pass Y and X and use the fit function. Let's run it. Then we can find the predicted values. So I define a variable named predictions, which is equal to model.predict. So to fit the regression model, we use the fit method, and to predict values, we use predict. Then we pass X. Now we want to look at the goodness of fit for this regression model, the coefficients, the p-values, and to see this, we can apply summary to the model, and now you can see the OLS regression results. Dependent variable is Y, method is least square, and you can look at the R square, which is pretty high, 0.97, because the function that we define is a linear function of X. And you can see AIC, Akaike information criteria, number of observations, and also the coefficients. So we have one independent variable, so we see just one coefficient. Then you see the T statistic p-value, which is pretty significant, and other statistical techniques here. So that's how we can use the stats model API and generate a summary of the regression models. Now, in our second example, we want to use the scikit-learn library. There are some data sets which are already uploaded to that library, and we can use that to train regression models. In this example, we are using diabetes data set, which consists of 10 physiological variables like age, sex, weight, blood pressure, etc. on 442 patients. So we have 442 observations and an indication of disease progression after 1 year. So there is one response or dependent variable. First, in order to import the data set, we need to load the data. So as you can see here, from sklearn.dataset, import load underline diabetes. And then we can create a variable which contain the diabetes data set. Afterwards, we want to divide the data into training and set samples. And to do that, we define several variables, as you can see here. 2 variables for X, 2 variables for Y. So diabetes X train. And in this example, let's say we want to use the first 30 observations for training the algorithm, and we use the rest for testing the algorithm. So it would be the same diabetes dot data, and the response variables are assigned under target variable. So diabetes dot target, the first 30 observations for training Y, and the rest is for testing the algorithm. Then we can fit a linear regression model. So from sklearn, we import linear underline model. So all linear regression models are defined under linear models. Then we create an object named regression. So linear underline model dot linear regression. Then we can, once we create this object, then we can apply fit or predict method. So I call this object regression.fit, and then we pass X and Y train. And if we want to see the regression coefficients, Then we call the model.coefficient, and then it prints all coefficients for the model. We can also calculate mean square error for test dataset. It means that we use the predict method to predict values for X test, and then we compare them to actual values, and then raised to 2, the average would be mean square error. Now let's implement this in a notebook, and you can see what the results look like. First, we need to load the data. So from sklearn.dataset, import load underline diabetes. And we define a variable named diabetes. And then we assign this data set to that variable, load underline diabetes. Okay, we are missing S here. Let's run it again, and let's print diabetes. So first off, you can see that it's an array, and it has 2 columns, data and target. So target is the response variable, and data is the independent variables, which is like a list of lists to define that array. Okay. Now we want to define the train and test samples. So we define 4 variables, diabetes, underline X, underline train. So here we divide data into train and test samples manually. Later on, we will use another method which randomly splits data into test and training samples. In this example, we choose the first 30 observations, diabetes dot data, first 30 for training purposes, and the rest for test. So another variable named diabetes, underline X, underline test. So we get access to the first column, diabetes data. Now the remaining is assigned to test samples. Okay, there is a typo here. Let's run it again. Okay, we do the same for Y variable. So we define 2 variables, diabetes, underline Y, underline train, which is diabetes dot target, because as you can see here, the data has, this data refers to independent variables, and target refers to the response variable. So diabetes dot target, and again the first 30 for training purposes and the rest for testing the model. So diabetes underline Y, underline test, target variable. Let's run it. And now we can import linear model. So from sklearn, import all linear models, linear underline model, and then we define an object because we want to specify which linear model we want to use here. So a variable named regression. First we call linear underline model dot linear regression function. Linear regression. Now we create this object, then we can apply fit and predict methods. So regression dot fit, then we can pass x and y. So the first variable, diabetes underline x underline train. The y variable is diabetes underline y underline train. Let's run it. Okay. Then we can print the coefficients. So we want to print regression dot all coefficient coef underline. Now you can see the coefficients for the independent variables. For 10 variables here, some are positive, some are negative. We can also calculate the mean square error for the test data. And we can apply the mean function under numerical Python library. First, we need to find the predicted values. So regression.predict diabetes x test underline x underline test. So we predict the values for this data set minus the actual values, which is diabetes dot target, which is saved under diabetes underline y underline test, raised to 2, as this is mean square error. Now we can run it. Okay, there is a typo, predict. Now let's run it again. Diabetes underline there is a typo here. Let's run it again. Okay, now this is the mean square error for the test data. So we subtract actual values from the predicted values raised to 2, and then we take the average, and that becomes the MSE for the data set. Now we want to talk about penalized regressions, starting with lasso regression. LASSO stands for Least Absolute Shrinkage and Selection Operated Regression Model. The difference is that the cost function is added for terms that are not zero. So if you look at this equation in this slide, the first term is the sum of a square error, just like what we had before, but also we have a second term, which is added for terms that are not zero. We call it L1 regularization. Lambda is a tuning parameter times the summation of all non-negative coefficients. Lasso regression performs both variable selections and regularization, and it can result in sparse models with few coefficients. Some coefficients can become zero and eliminated from the model because of the second term that we added to the cost function. Overall, lasso solutions are quadratic programming problems, and the goal of the algorithm is to minimize this function. Now, let's apply lasso regression to the diabetes dataset. Just like before, we import a linear model, then we create an object to specify which linear model we want to use. In this example, linear underline model.lasso. But as you saw in the cost function, we need a tuning parameter, lambda. So we need to pass the value for that tuning parameter, and here alpha equal to 0.1 is the tuning parameter. So this can be chosen arbitrarily. In practice, we use some cross-validation techniques to find the best value for this tuning parameter. Then we call the object, we can apply the fit and predict methods, and we can print the coefficient. Let's run it and then compare the coefficients for lasso regression to those of linear regression. So when we applied the linear regression, we had 10 non-zero coefficients. So now let's create another object. Let's say regression 3. First we call linear underline model dot lasso. So we are going to apply lasso method. But we need to also pass the value for lambda or the tuning parameter, which can be done by defining alpha 0.1. Then we can call the object dot fit. Then we pass the training samples for both x and y. So diabetes underline x underline train and diabetes underline y underline train. Great typo here. Okay. Now let's look at the coefficients. So we print the coefficient, all coefficient in the model. Now you can see that some coefficients are 0. So that's in terms of coefficient, you can see the difference between the result of lasso regression and the linear regression. Another pairwise regression is called ridge regression. Ridge regression is a way to create parsimonious model when the number of predictor variables in a set exceeds the number of observations, or a data has multicollinearity, correlation between predictor variables. Here you can see the cost function. The first part is similar, which is the loss function or the sum of a square error. Then you see the second term that we call L2 regularization. So it's added for large coefficient. So now you can see lambda times the summation of beta squared. So in other words, this term shrinks the coefficient. And that's why we say this regression model generates parsimonious models and can handle multicollinearity in data. Now we want to apply ridge regression to the diabetes data set and print coefficients. So the method or the ridge function is defined under linear model. Again, we need to pass a tuning parameter lambda, and then we can apply fit and predict methods and look at the coefficient. Let's run it in a notebook, and we print the coefficient. We can compare the result of this regression model to that of lasso regression, for instance. So I create another object, regression 2. So we call linear underline model. This time we apply ridge and alpha equal to 0.1. Now we call the object regression 2. We apply fit method. Now we pass diabetes underline x underline train and the target values diabetes underline y underline train. Let's run it, and now let's print the coefficients. And you can see the result for, let me see, the result for the ridge regression if you compare it to the lasso regression, you can see coefficients. All coefficients are non-zero, which is not the case when we go with lasso regression. But if you compare the coefficient to the linear regression coefficient, you can see the first variable coefficient is minus 146, but here it's minus 16. So that's because ridge regression shrinks the coefficient, and if you compare other coefficients as well, you can see the difference. For example, the fifth variable here, the coefficient is only 26. Now, I would like to discuss ElasticNet, which is another linear regression model, which is a combination of lasso regression and ridge regression. It means that the cost function linearly combines the L1 and L2 penalties, as you can see in this slide. So we have two tuning parameters. We can use the linear model to import ElasticNet, and when we create the object, then we can apply the fit and predict methods. Now let's quickly apply this to the diabetes data set. First, we import ElasticNet. So from sklearn dot linear underline model, import ElasticNet. Let's run it, and then we can create an object. Let's say regression 4, which is the ElasticNet. Then we can apply the fit method. So we pass X and Y, diabetes underline X underline train, and the target values, diabetes underline Y underline train. Now we can print coefficients, print regression 4 dot coefficient, and you can see the results. Some of them are 0, some are positive, and some are actually one is negative. The last regression model we are going to discuss in this lecture is logistic regression. Logistic regression, despite its name, is a linear model for classification and prediction. Logistic regression is also known as a log linear classifier. In this model, the probabilities describing the possible outcomes of a single trial are modeled using a logistic regression. In this slide, you can see the math for linear regression, for logistic regression. Logistic regression is a function of an odds ratio. The odds ratio represents the effect of a predictor X on the likelihood that one outcome will occur. And you can see the cumulative distribution function for logistic regression in this figure. Now let's apply logistic regression to the student pass-fail dataset. I have already uploaded this dataset to Canvas. The data has 3 variables, and it's from the UC Irvine Machine Learning repository. The first variable is self-study daily, which indicates how many hours the student studies daily at home. The other variable is tuition monthly, which shows how many hours per month the student is taking private tutor classes. And the last variable, which is a target variable, pass or fail, indicates pass, so it's equal to 1, or fail, and it's equal to 0. So the target variable is a binary one. Now, if we want to apply logistic regression to this data set, it's a CSV file. So first we need to upload it to the notebook, and then we can use read underline CSV method and create a data frame. As you can see here, after we create the data frame using pandas library, if you use the head method, you can see the first 5 observations in your data set. Now we want to differentiate between independent variables and response variable. So we can use the drop method to the original data frame and drop pass or fail column. So everything else would be the independent variables or features. And then the last column, pass or fail, we will assign it to y variable, which is the response variable. And the next step is to split data into training and test samples. And here we are using the train test split method, which randomly splits data. I would like to draw your attention to some new libraries we imported in the beginning. So from scikit-learn, we import metrics. So you can have different accuracy metrics for your model. From the scikit-learn library linear model, we import logistic regression. And the third one is from the scikit-learn.model_selection, we import train_test_split. And that's the method that we use to randomly divide data into test and training samples. By default, it assigns 75% to training and 25% to test, but you can change this default. In this example, we go with default values. So I define 4 variables, xtrain, xtest, ytrain, and ytest, and then I apply this method and pass x and y. Then we define an object, assign the logistic regression. When we define an object, then we can apply the fit and predict methods. So I call LR, my object, apply fit, and pass xtrain and ytrain. We want to print the coefficient, and also we want to predict values for our test sample and evaluate its accuracy. But this time we want to use the accuracy score defined under metrics library. So metrics.accuracy underline score, and then we pass two values, the y underline test, the actual values, and the predicted values. Now let's implement this in a notebook and we can see the result. First, from the scikit-learn library, we import metrics. sklearn import metrics. Also, we want to import logistic regression, so it's defined under sklearn.linear model, linear underline model, and we import logistic regression. We also want to use the model selection and the functions defined under that library. So from sklearn.model_selection, we import train_test_split. So here, this is the data set. So it has 3 columns: self-study, daily, tuition, monthly, and the last column, the binary variables, is 0 and 1. So it's 1 if they pass and 0 if they fail. So I have already uploaded that data set here, as you can see. And now I can use the read_CV method to create the data frame. So df is equal to pandas.read_CSV. And then we pass the file name, which is student-pass-fail-data, and the file extension is CSV. Then we create the data frame. Now we want to see the first 5 observations, so we can apply the head method. So you can see there are 3 columns and for the first 5 observations. Okay. Now we want to define the first 2 columns are independent variables. The last one is the dependent variable. So I define 2 variables, x and y. X is equal to data frame. Then we apply the drop method. We want to drop the last column, which is pass underline or underline fail we pass axis equal to 1, and then if we print, then we have a data frame with only 2 columns. And y is equal to the last column, so df dot pass underline or underline fill. And if we print y, you can see it's a data frame with only 1 column. Now we can split the data set into training and test samples. So I define 4 variables: x underline train, x underline test, the same for the y variable, y underline train, and y underline test. Then we call the train test split method train underline test underline split. Then we pass x and y. 75% assigned to training and 25% is assigned to test sample. Now we can create the logistic regression model. So define a variable or object LR. I assign logistic regression. Now I can apply the fit and predict methods. So LR.fit, then we pass X train and Y train. Because we are working with supervised learning algorithms, we have target values. Now we want to print the coefficient. So LR.coef underline. And you can see there are 2 coefficients because we only have 2 independent variables. We can calculate predicted values. Y underline predict is a variable that I define. So LR.predict, we pass X underline test. So there is a typo here for predict. Let's run it again. Another typo, X underline test. Let's run it. And now let's print the predicted value. We expect to see binary variable 0 or 1. So you can see it's an array for our test sample, all 0 or 1. Now we want to evaluate the accuracy of a model, and that's where we can use metrics. So I define a variable named accuracy. I call metrics. Then there is the accuracy score, accuracy underline score method, and I need to pass the actual values, y underline test, and the predicted values, the result of the model, y underline pred. Then we can print accuracy, and you can see this model accuracy is 97%. And with this example, wrap up our discussion about regression models.